Hello and welcome to the first section of the course called Motion in 2D. The first topic of this section is projectile motion, which we will split over a number of presentations. This is part 1. At the beginning of each presentation, we'll take what's required from the SACE learning outcomes and put them onto the slides so you know exactly what the presentation will cover. And you can see the 4 points here are listed on this slide. So first we'll define what projectile motion is. So a projectile is an object that has been launched at some angle into the air near the surface of the Earth. So the motion of this projectile is a curved path, which is in the shape of a parabola. When the object is near the surface of the Earth, and it doesn't move very far away from that, we can assume that the force of gravity on the object is approximately constant. Air resistance opposed to the motion of a projectile can occur, and this will change the flight of its path and the shape of its path. In most of the course that we're going to be looking at, we will neglect air resistance, but only discuss it at the end. So we'll continue with another definition. We'll define vectors and scalars. So a scalar is a quantity that has magnitude only, but has no direction. So an example of this would be mass, time, speed, and distance. All of these quantities only have a size. A vector, however, is a quantity that has both the magnitude and direction. So an example of this would be acceleration, force, velocity, displacement, all where direction are important. So vectors are typically designated by writing them with an italic type character or placing an arrow above the letter which denotes the variable. It is important to realize the difference between vectors and scalars, and an example I will use is speed and velocity. So both quantities, speed and velocity, measure how fast an object is moving, but speed does not include the direction of the motion, whereas the velocity does, being a vector quantity. So using this in a very specific example, if we have a highway where we've got cars traveling at 60 k's an hour, we can say that the speed of the cars is 60 k's an hour. There are cars traveling in different directions though, so some cars might be traveling north, some cars might be traveling south. So we can't say the cars have the same velocity because they're traveling in opposite directions. So that's the distinction between the scalar and the vector. Vectors will often be represented by arrows, with the length of the arrow representing the magnitude of the vector quantity and the direction representing the direction of the vector. So vectors can be broken up into two component vectors. So what this means is, by looking at that diagram below, we have a vector which is labeled R, and it can be broken down into two components. One is directly up and one is pointing to the left. Now these component vectors are actually perpendicular, and what this means is that they do not affect each other and that they are independent. Following on from breaking down vectors into their components, we can add two or more vectors together to give a resultant vector. Now vectors can be drawn and added together by drawing them head to tail. So in this case, vectors don't even need to be perpendicular to be added. So a vector can also be subtracted from another by reversing the direction of the vector to be subtracted, then adding it onto the end of the other vector. So let's have a look at what this might look like. So all vectors can be represented geometrically, meaning we can draw it by a line segment. So when we add vectors, for example, we add vectors A and B, we can see we've got vector A pointing in a downwards direction, vector B in an upwards direction, and when we add them together, we get the result C. So focus on A and B first in the triangle, and then what we're left with is our result, which will be C, which will be from the beginning of A to the end of B. So let's look at an example where we add 3 or more vectors. So looking at the vectors on the left, we have 4, which are A, B, C, and D. And each of the lengths and direction are significant. So when we want to add these 4 vectors together, we can look at the one that's been put together on the right, and we start at an arbitrary starting point, but if we wanted to start with A, we would add A first. Then at the end of A, we add vector B. At the end of B, we add vector C, and at the end of C, we add vector D, and we end up over here. Okay, now the result is the resulting vector from the start, which is at the beginning of A, to the finish, which is at the end of D. Now this vector is represented on this diagram as vector E. Okay, so there's a lot going on in this diagram, this animation. So to slow it down, you could replay this video, or you could have a look at the slides where the animation just loops. But what you can see is we're adding 5 different vectors, A, B, C, D, and E. And in each case, in the 3 examples at the bottom, we're adding them in a different order. What I want you to focus on is the result, which is the vector R, which is in green. So focus, no matter what order that we add them in, the result is the same. And this also links in with mathematics, where when you add numbers, it doesn't matter what order they're in, you'll end up with the same answer. So we'll be looking at projectile motion in 2 dimensions, but to analyze it, we can make it simpler for ourselves and just focus on the components in each dimension. So those dimensions are typically horizontal and vertical. So we can use the techniques. We can resolve the motion into 2 perpendicular 1D motions, and we treat these independently of each other. So we can consider the motion to be the combined effect of 2 independent motions. And as mentioned, one is horizontal and one is vertical. On the diagram at the bottom, the vertical motion is represented with a red arrow and the horizontal motion with a blue arrow. So I mentioned earlier we can break projectile motion up into its components, and first we're going to have a look at the horizontal component. Okay, so consider the following multi-exposure image of projectile motion. So we've got a guy on a motocross bike traveling off the ramp on the right into the air and then landing on the left. Okay, the time interval between each exposure is constant, and you can see that by the blue lines that are drawn in. So this is a photo, but when we draw the lines in, we can see it's still constant. So notice that the path followed also by the rider is parabolic in shape after it has left the ramp. So the only effect really on the rider is the force of gravity. So using those vertical lines, we can measure the horizontal distance between each exposure. And we can see that the projectile travels equal distances horizontally throughout the motion. Therefore, we can assume that the horizontal component of the velocity of the projectile remains constant when the projectile is in the air. So why exactly is the horizontal component of velocity constant? So once the object has been projected into flight, the only force acting on it is gravity. And this gravity acts directly downwards towards the center of the Earth. So therefore, the acceleration of the object must also be in this direction. Now, as the acceleration is down and there are no other forces acting in the horizontal direction, there can be no change in the horizontal direction. So the horizontal velocity remains the same, it remains constant. Now let's look at the vertical velocity component of our motocross rider in flight. So it's the same image. This time, look at the vertical spacing between the successive images, specifically the distance traveled between each image. So looking at image 1 and 2, we can see the distance that's been displaced or translated is this distance here, and you could say it's large. Whereas if we look at points 3 and 4, the distance of displacement is very small compared to what it was originally. So as the rider leaves the ramp and travels to its peak, the distance between successive images decreases. As the rider comes down from its highest point, the distance between successive images increases. Thus, we can say the vertical distance traveled between images it varies. If we know the magnitude and direction of a vector, we can actually calculate its components, being the vertical component and the horizontal component. This is easy using trigonometry or Pythagoras when there's right angled triangles, and when the vertical and horizontal components are perpendicular, we can do this. So you'll find these equations on your formula sheet if you want to look for them as well. But to find the horizontal component, which on our diagram on the left is the horizontal component of our vector A, which is in the middle, and we denote it as A with a subscript X. We can also use the subscript of H for horizontal. Okay, but the formula is AX is equal to A, which is the magnitude of our original vector, times cos theta, where theta is the angle between the horizontal and the vector. We can also find the vertical component, which is denoted by AY, Y being the vertical component, but we can also write it with a subscript V. And this is given by AY is equal to A sine theta. One of the requirements of SACE is to analyze a multi-image photograph of a projectile. So our projectile is denoted, I'm drawing with red dots, in the middle. Okay, and we can analyze its components, being the horizontal and vertical, using a diagram like this. So the horizontal component of the velocity can be noted by these the white or empty dots at the top, and we notice that they're constant, meaning the spacing between each dot is pretty constant. It's not really changing, and that coincides with the theory that we discussed earlier. Now if we have a look at our vertical components, you can see the spacing between each successive image is actually increasing. The distance is increasing. And this is actually due to gravity, because the object is actually getting faster and faster as it falls, because there's a force on it. What I'd like you to do now is to pause the video, grab some pad paper, and recreate this drawing on the paper. Then, on the diagram, draw the vectors to represent the velocity and acceleration of the projectile at any instant in its components. So for each dot, show the vertical component, the horizontal component, and the resultant component. Okay, pause the video once you've finished, because I will show the answers on the next slide. Okay, so you can see on this diagram that we've got here, if we look at the horizontal component at the top, we're only showing horizontal arrows, because that's the only component of velocity that we're looking for at the top. Along the left, we've got the vertical component, and you can see we're only showing the vertical component of velocity. And notice, so going from red to pink to purple to green, that the magnitude is getting larger every time. And this signifies that the magnitude of the velocity is increasing. For the projectile as it's going through the flight, we've got our horizontal component, which matches our top line. We've got our vertical component, which matches our lines on the left, our vertical lines. And our result is the addition of these two. So you can see as we're going along, the resultant velocity is changing direction due to the components. And you can see it's forming the parabolic shape. Okay, we're going to do another question now, so I'd like you to pause the video and write down the question in orange. So a projectile is traveling at an angle 40 degrees above the horizontal, with a horizontal component of 6 meters a second. What is its velocity? So what we do, rule number one, is to draw a picture. So we've got the horizontal component, which we know, which is 6 meters a second. We know this angle here, which is 40, and what we want to know is V. Okay, so pause the video and have a go at it. Come back when you feel like you've got an answer. Okay, so to do this, we know that because we use our formula where the horizontal component is equal to the velocity which is the resultant velocity, times cos theta. So rearranging this equation, we can find that the final velocity is equal to the horizontal divided by cos 40, or cos theta, and we get our answer of 7.8 meters per second, and that's in the horizontal direction, in this case being to the right.